All right, we're going to consider the first thing that influences or affects the rate. And the first thing that influences the rate is concentration. So if we have some reaction, and really all that matters is what the species are in the reaction, because unfortunately it doesn't matter what the stoichiometric coefficients are. The reaction dependence or the rate law can only be determined experimentally, meaning this value of 2 doesn't tell you anything, which is kind of disappointing. So with this in mind, if we've got this reaction, we are going to ignore the products, and we're going to ignore the products because they just build back in again and confuse everything. So we're going to try to work close enough to when the reaction starts. This is called the method of initial rates, so that there aren't any products and we can only consider the reactants. If we have this reaction, we are going to say that our rate should depend on the concentration of A, and it should depend on the concentration of B, and we're going to multiply these. We're going to put a constant in front, which is our little k. This is our rate constant. As we keep going, we're going to discover we're going to put the temperature dependence in rate constant, because we don't want to change these rate laws every time we change our temperature. And we're going to say that these values of 2 and 1 don't help us, and we're just going to say that it's going to be dependent on some value x and y. Our job is to go to the lab and get enough data that we can take and we can find x, y, and k. This right here, experimentally determined equation, is called our rate law. When you're ever asked for a rate law, it means you're going to write that the rate is equal to K. You're going to take the concentrations of the reactants, multiply them together, and they're going to be raised to some power, which you have to find experimentally. So these are always determined experimentally. For any reaction, if we have two reactants here, they're going to be K times the concentration of A to the X and B to the Y. We're going to ignore the product consistently and only look at it in terms of reactants. And unfortunately, again, this number is not related to this number. So the X and the Y have to be determined experimentally. Let's consider what these might mean. If we take a look and we have a rate and we have, say, a value of A, and if we change A and it doesn't change the rate, so if A goes up and the rate is the same, then in fact the rate doesn't depend on A, and we say that the reaction is zero order with respect to that reactant, meaning that the rate would equal K times A to the 0, telling us that the rate is unchanged if the reactant changes. Now, if they are 1 to 1, if you go 2A and your reaction goes into 2 times as fast, then these guys are 1 to 1, and our order is going to be first order, and our rate would equal K times A to the first power. If instead it quadruples and we take and we get 2A and we end up with 4 times the initial rate, that's going to be like A squared, and our rate is going to equal K times A squared. So if our rate is quadrupled and our reaction is gone up by a factor of 2, we say that this is a second order reaction. If we have two reactants that are changing, we add up the values of x and y, and we are going to get an overall order. So each of these individual values, the 0, the 1, and the 2, are the order for that element or that reactant. The sum of them is the overall order. All right, so we get our rate law and we get our x and y from experiment. We're going to calculate our k value. Now the units of k depend on the overall order, that sum of the x and y, for this reaction. One way of doing this is to just take and plug in your numbers and solve for k. That's what I do. On the other hand, if that doesn't work for you, our units for k are going to equal molar, the units of concentration that we tend to use, times 1 minus overall order divided by seconds. So if the sum plus x and y, let's say x plus y, is equal to 2, then our k will equal or have units of molarity of 1 minus 2 divided by seconds. This is going to be molarity of the minus 1, and K will have units of per molar second. All right, that's one way. We'll do it long ways as well. So a rate law can only be determined experimentally, which means that you are going to go to the lab and you're going to collect data. Now, the first thing you're going to notice is you are not going to want to change all of your reactants at the same time. So what we consistently do when we try to find rate laws is we hold a reactant constant and let something else vary. So notice this one here is unchanged, and this value here goes up by 2. And then we see if that has any effect on the rate. So we look at our rate, and our rate tells us that if we go from here to here, it also goes up by 2. Well, 2 to 2 is the same as 1 to 1, and 1 to 1 is first order. So if 1 to 1 is first order, this tells us that our rate is going to depend on the concentration of the iodide raised to the first order. And we can do the same thing with the S2O8, 2 minus. And if we do that, we're going to want to hold something else constant. So we're going to look and compare these two runs right here. And we're going to look at what happens to the rate if we change the concentration of the S2O8. Well, if we do that, we realize that from here to here, it goes up by 2. And again, we're going to use that because the iodide is constant. When we go to our rate, we see that the rate is also going to go up by 2. And this tells us that the rate is going to be proportional to the concentration of the S2O8, 2 minus, also raised to the first power. Again, how do we know? Because we have a proportionality of 2 to 2. 2 to 2 is the same as 1 to 1, which tells us that it's first order. So the overall reaction, or the order for the overall reaction, is 1 plus 1, and that is going to be second order overall. And we're going to say that our rate is going to equal K multiplied by the S2O8, 2 minus, raised to the 1 power, times iodide raised to the 1 power. And the only thing left that we have to do is solve for K. All right, there are multiple different ways of doing this. So another way to do this is that instead of taking and doing it by looking at just the rates, we can actually do ratios. And we can take the ratio of run 1 over run 2. Now, why do I want run 1 over run 2? Because I always want a larger number on the top so I get whole numbers, hopefully, and not fractions. We know that our rate law says that the rate is equal to K multiplied by the thiosulfate multiplied by the iodide, and that this is some value of X and this is Y. And we're going to take and do a ratio of the rate at run 1 over run 2, and we're just going to take and put these two equations over top of each other. What would that look like? Well, this would be 2.2 times 10 to the minus 4 units of molar per second, run 1, over run 2, 1.1 times 10 to the minus 4 molar per second is going to equal, and then we're just going to do the left side of this equation, K times S2O8 2 minus to the X times I minus to the Y divided by K times, and this would be the value here at run 1, and we can actually plug numbers in here. So if we think about this, instead of doing this, we're going to set this equal to our value of K times 0.08 multiplied by 0.034. We're going to include our x's and our y's, divided by K times 0.08 to the x times 0.017 to the y. And our other side over here is going to be the 2.2 over the 1.1, and that's just going to go out to 2. Now let's cross off what repeats. We have k's, cross them out. R.08x crosses out, and now we see that the change in the rate only depends on the change in the iodide. Well, because these two values are raised to the same exponent, we can say that 2 is going to equal 0.034 divided by 0.017 raised to the y. Well, this is going to say that 2 is equal to 2 to the y, and y is going to equal 1. You could do that the same for both of them, and once you do that the same for both of those, you can get the same thing we got before, and you'll get that rate is equal to k times S2O8, 2 minus, times I minus, both of these raised to the first power. So you want to find k. To find k, we are just going to go to one set of data and plug in our values. So to do that, let's look at it, and we're going to take, for no particular good reason, we're going to find k, and we're going to use run 2. You could use any run you want, but if I used run 2, I'd get 1.1 times 10 to the minus 4 molar per second is going to equal k times 0.08 molar times 0.017 molar. And if I take and I do the math on this one, I'm going to get a value of k is equal to 0.0074. Because our units here, or because our overall order is second order, this is going to have units of 1 over molar second. I know that's hard to read, so I'm going to go down here and do it one more time. And our final equation is that rate is equal to 0.0074 units of 1 over molar seconds times the concentration of S2O8, 2 minus, times iodide to the minus 1. And this is the rate law. And the rate law has to be experimentally determined, and you have to have a K, and you have to have the units on the K. All right, let's do another one. So if we do another one here, let's compare A and B. We know we have to ignore these the 2 there. In some ways, it's almost better to do these without even seeing what the balanced reaction is, because then you aren't tempted to use that stoichiometric coefficient as the order. But we're going to take a look at holding one of them constant and changing the other. Here, if we hold A constant and change B, we know B goes up by 2, and the rate is going to go up by a factor of 4. And you know this because 48, or 0.048 over 0.012 is equal to 4. Well, what does this tell us? This tells us that 2 times b is going to be a total of 4, which is the same as 2 squared. And if we take and we change this by 2 and quadruple it, then what we're going to say is that our order with respect to b is b squared. Or if we take a look and do this longhand, so let's do this, actually let's finish this one, then do it longhand. So here we go. This way tells us the rate is equal to sum k times a times b squared. We need to find out a as well. A, we're going to take a look, and we're going to find a by using 1 and 3. We're doing 1 and 3 because if I go to 1 and 3, a is going to go up by 2, and our rate here is going to go up also by 2 from 0.012 to 0.024. It tells us that as our rate goes up by 2, our 2a is equal to 2 times the rate. It says that these are 1 to 1, which tells us that it is first order with respect to a, giving us that rate is equal to k times a times b squared. And our job would be to find k. Well, if we want to find k, we just pick a value. So let's take run 3, again, for absolutely no good reason, and see if we can find k. So if I take my numbers, 0.024, using the rate from run 3, molar per second is equal to k, multiplied by the concentration of A, which is 0.50, multiplied by the concentration of B squared. I will plug in the math here and discover that 0.024 divided by 0.5 divided by 0.1 squared is going to give us a k of 4.8. The overall order is 3, and our units are going to be 1 over molar squared second. So that is the shorthand. Let's do it longhand as well, make sure it makes sense. All right, so let's do the same one longhand. Again, to do this, we have to hold one of these constant, vary another, and compare it to the rate. We're still going to start with rate is equal to some rate constant multiplied by the concentration. This is A. We're going to raise it to some value X. You can use any variable you want, times B raised to the Y, and our job is to find X, Y, and K. To do this, we've got to hold some stuff constant. So I'm going to compare run 2 over run 1. And I'm going to do run 2 over run 1 because 1, A is constant, and B, I'm going to put the larger number on the top. So 0.048 molar per second divided by 0.012 molar per second. And again, plugging it directly into this, just putting the numbers in there. We don't have a value for K, so it's still going to be K. Plugging in the concentration for A for run 2, and that's 0.25 raised to the X. It's constant, so it's 0.25 in run 1 as well. And then I'm going to go to the B value. The B value in run 2 is 0.20 to the Y over 0.10 to the Y. So what happens here? This value is 4. Our K's cross off, our values of A cross off, and I'm going to combine the inside terms, and I'm going to get 4 is 0.2 over 0.1 raised to the Y, which tells us that 4 is equal to 2 the Y. What do I have to do to 2 to get 4? I have to square it. So Y is 2. And the rest I can do the same way. So you have two options. You can either do a direct comparison and take a look at it and see what it does. Please note on the exams, these are not going to be really weird ones. You might get a homework problem where these could even be like a 1/2 or a cubed. But for the exams, they're going to be fairly straightforward. Either method works. Make sure you calculate your K.